Hello everybody, hope you're all keeping well and safe at home. Today's physics lesson is all about resultant forces, and our objectives today are: I can state and apply Newton's first law of motion, I understand what a resultant force is, and I can explain what a resultant force of 0 newtons means. That last objective there, that's quite a tricky one. So in the last few lessons we've been learning about scalars, vectors, drawing scaled free body diagrams, looking at Newton's third law and understanding action-reaction pairs. So today we're just going to consolidate this into the form of resultant forces, and you're going to be answering some GCSE exam style questions which you're going to have to email your teacher. So let's look at Frome. It's where most of you live. You know extremely well. What would it be if you could build a theme park right in the middle of Frome, right on your doorstep? So whereabouts would you build it? Would you build it in the fields? So just outside Frome, it could be away so you wouldn't be interfered by traffic and all the people, but you could still see. Would you put the theme park over in the Manor Estate? Put it slap bang in the middle of Frome town itself. Well, if you look at the size of Alton Towers, it's actually about the same size as Frome itself. I'm sure you know these really, really well. You've got Oblivion, Air and Smiler, which has been in the news for all the wrong reasons recently. It's about a 3.7 square kilometre area, so it's not actually that big. They cram a lot of roller coasters in a small space, but about the same size as Frome. And if you look at the GIFs, you can just sit there and watch most of them over and over and over again, can't you? This guy here, he's called Donnelly Williams. I can't show you the video, but I've given you the link at the bottom. So at the end of the video, why not go back, click on it, and see what job he's got and what he does. Now, he uses a lot of physics and a lot of maths for his job, but I reckon it's one of the best jobs in the world. I wish I had his job, and I'm sure if you watch the video and see what he does, I bet a lot of you would want to do his job too. But it's just interesting to see how this relates to real life and what jobs can you do with this area of physics. As I say, he's got one of the best ones, I think. So let's look at Oblivion and let's do some physics. So I think that the gravitational force pulling the roller coaster downwards is 5,000 newtons. So because force is a vector quantity, easy to remember, for force, for vector, it has two pieces of information. We learned about this last lesson. It has a magnitude and also a direction, and that's what constitutes vector quantity. So we have the arrow pointing downwards towards the centre of the Earth, which is the core, and we have the number with the magnitude 5,000 newtons. And I think that if you were on Oblivion and you went downwards, there would be some air resistance, and I reckon that would be about 1,500 newtons. And because it's an oppositional force, it's pushing up against you. So we've got 5,000 newtons going downwards and 1,500 newtons pushing upwards. So to work out a resultant force, which is what this lesson is all about, all we've got to do is get the big number, take away the smaller number. So we do 5,000 minus 1,500 newtons, and that gives us 3,500 newtons altogether. So resultant force really is the result of all the forces acting on a body. And we end up with 3,500 newtons, and that just means that there are 3,500 newtons more going downwards than there are upwards. So 5,000 take away 1,500. I suggest you pause the video and you write down into your book the words on the left-hand side. A resultant force is the result of all the forces acting on a body, and this is called the resultant force. This can be represented just as an arrow, so downwards. You'll see that it's shorter than the 5,000 newtons one, and that's because this needs to be scaled. And because force is a vector quantity, you need to put the magnitude as well. So we have the direction of the arrow going down, so it's 3,500 more going down, and we write down the number, the magnitude underneath it. So let's look at this roller coaster. So I've got 3,000 newtons pulling the roller coaster upwards. So I'm sure you've been on a roller coaster. At the beginning, the roller coaster has to get up, and there's like a crane or a pulley system, and a rope kind of pulls the roller coaster upwards. So I estimate that to be about 3,000 newtons. But we're going to have some oppositional forces acting on the roller coaster too. So I imagine 500 newtons of air resistance and 1,000 newtons of friction. And because they're opposing the forward motion, we have them going in the opposite direction. We have them going backwards. And to calculate the resultant force, we're going to start with drawing a box and arrow diagram that we looked at last lesson. So that box there represents the roller coaster, and I need a scale and a ruler. So my scale is going to be, for every centimetre, 500 newtons. So the forward force is 3,000 newtons, so 500 newtons is 1 centimetre, 1,000 is 2 centimetres, and so on. We end up with 6 centimetres, because 500 goes into 3,000 6 times. Now I need to draw on the air resistance and the friction. So the air resistance was 500 newtons, so that's only 1 centimetre, and the friction between the wheel and the roller coaster track is 1,000 newtons, and that's 2 centimetres. So there's my box and arrow diagram with all the forces and direction and magnitude all labelled on it. So to calculate it then, 3,000 newtons going towards the right, and I've got 1,000 and 500 going to the left. So altogether 3,000 to the right and 1,500 going to the left. Big number take away small number. So 3,000 take away 1,500, and I have 1,500 newtons going forward. Now it's really easy to see if it goes forward or backwards because it's a positive number. If it was minus number, it would be going to the left. But because this is a positive number, we can see it goes forward. And I'm sure you can figure out that 3,000 is 1,500 more than 1,500 added together. So we get our ruler again, we scale it, 500 per centimetre, and 1,500 would be 3 centimetres long. So we would write 1,500 newtons forward, and then we would scale that arrow to show the direction. And that's that done. So your turn now. Here are 3 questions. And to help you with the third one, I've added a picture for you as well. So what I'd like you to do is to pause the video and have a go at answering these questions. Okay, let's look at the answers. I haven't drawn the arrow and box diagrams for this one because I didn't know what scales all of you would be using. I'm sure you're all going to be using different scales. But the resultant forces itself, for number 1, is 1,500 newtons going forward, 2, 1,500 newtons going to the left, and 3, 14,000 newtons going downward. So give yourself a few marks for your numbers, the magnitude, and if you've scaled the directions, then really, really, really well done. Tick those off as well. Okay, so looking at our third objective today, what happens when a resultant force is 0 newtons. So far, all of our resultant forces have all been a number. So let's see what happens when it's 0. So this is Rita, Queen of Speed. Hopefully some of you have been on this before the lockdown. It's one of my favourite rides. I love this one. It's really, really, really fast. You're just waiting there, then a big electromagnet kind of charges up, and then it releases you and you shoot off incredibly fast. So when you're waiting, it's not moving forward. So the forward force is 0. And because it's not moving, there's no air resistance going backwards, there's no friction going backwards because you're not going forwards. So forwards and backwards, nothing's going on. You're stationary. The one at the bottom, so this time Rita, Queen of Speed, is moving. Its forward force is balanced by all the oppositional forces. So your forward force is balanced, it's equal to the air resistance and the friction. And again, we end up with a resultant force of 0. But this time, it's not stationary, it's travelling at a constant velocity. And this confuses students. Is 0 newtons, how do you know if it's stationary? How do you know if it's constant velocity? Why is it not accelerating, etc.? So let's have a look at this. So box and arrow diagram again really helps us out. In this image, Rita isn't moving. Okay, the roller coaster is not moving. So there's 0 newtons going forward, and there's no oppositional forces acting in the opposite direction to the forward motion. So there's no air resistance, there's no friction working against the forward motion. So 0 newtons forward, 0 newtons backwards. So we end up with 0 newtons altogether. So if it's 0 newtons, it's not moving. Okay, it's stationary, and stationary means not moving. You're just standing still. So that one I think makes sense. And you can see the people on the roller coaster, they're not moving forwards or backwards. They are all sitting there, all sitting nice and still. They're nice and stationary. So let's look at it when it is moving then. So we use our box and arrow diagram again. So in this case, I've got 3,000 newtons going forwards, going to the right, which represents for me going forwards. And I've balanced this with air resistance and friction of also 3,000 newtons are going in the opposite direction. As before, you take the numbers away from each other and we end up with 0 newtons. So what does this mean? Well, we've got 3,000 newtons going to the right and 3,000 newtons going to the left. If the arrow going to the right was longer and there was more force, then the roller coaster would actually be accelerating. It would have a positive resultant force and it would be accelerating. If the number underneath going to the left was larger, then it would have a negative resultant force and it would actually be decelerating. But because they're the same, it can't accelerate or decelerate. So it continues to move at the same velocity, at a constant velocity. So what I've written here is this time the roller coaster is already moving. The forward force is balanced by all the resistive forces, so that, the air resistance, the friction. It can't speed up, it can't slow down, so it continues to travel at a constant velocity. So we can thank Isaac Newton again for this. Very, very clever, very forward thinking. And I suggest in the moment you pause the video and you write down some definitions. So he said a resultant force is 0 if the object is stationary, then it will remain stationary. So if the object isn't moving, you calculate the resultant force to be 0 newtons. If it's already stationary, it will stay stationary. It won't move. To me, that makes perfect sense. So if I put a cup on a table and I leave it, it's stationary, it's not moving. It will stay not moving until I force it to move out the way. I grab it, I pull it, I push it, or I move it somewhere else. So if all the forces acting on it are 0, it remains stationary. However, if the object is already moving to begin with, and that's the bit that students always struggle with. If the object was already moving to begin with, and the resultant force is 0, it will move at a constant velocity. Okay, so if the object is standing still and the resultant force is 0, it stays standing still. If the object is moving and the resultant force is 0, it continues to move at a constant velocity. And there's the bit there that I suggest that you pause the video, and that's the bit that I would be writing down into my book now. Okay, this is known as Isaac Newton's first law of motion. Last lesson we looked at the third law of motion, and that's it for today. So all you've got to do now is have a go at these quick questions. There's 16 marks and there's some multiple choice ones in there. So this really shouldn't take you more than about 10 minutes to complete. And if you answer the questions, and then you can email it to your teacher, and then you'll have your teacher is able to mark it and offer you some feedback next week. And then for the postcard physics we've been doing, again, just summarise the lesson using a half-page template so that you've got some revision notes. And I know some of you be really interested in the roller coasters, and you'll look at Donnelly Williams and you'll watch the video and you think, wow, I wish I could do his job. Well, there's some extra tasks here that you might want to do to get you a bit more interested in roller coasters and how physics works in real life. Now, if we were actually in a classroom situation and not learning from home, this is the homework that I would give you for this week. It's optional, you don't have to do it, but I know lots of you will want to do this. So I hope you've learned something today and you've enjoyed that. Until next time, take care.